Okay, so we should be good now. So today, okay, so in the last two lectures, I want to change topic. So today's lecture, I want to talk about rationality in families of varieties. Okay. So just to fix notation, for me, a family will be a map F from X to T. So will be a projective and flat. Onto T finite type. The parameter space is a scheme of finite type and maybe also reduced. And we keep working over the complex numbers. And then the fibers are varieties, at least maybe the closed fibers are varieties. So I say geometry. So the closed fibers are varieties, and then of course you want that will imply also the fibers of non-closed points will be the same. So we're interested in looking at the following locus, called the rational locus. Given a family, I look at the points in the base such that the fiber is geometrically rational. So that when you pass to the algebraic closure of the residue field at T, it becomes a rational variety of algebraic closure. And then the question is, what is the structure of this set? In general, you want to have this word geometrically rational because you could have, for instance, the path of vibrations of a curve where every closed fiber is rational, but the generic fiber is not rational because of the field. But if you pass to algebraic closure of the function field, then it becomes rational, of course. It becomes another Despezo surface. So in order to get a good structure theorem for the rational locus, you really want to define it this way. So the main theorem that we're going to focus today is the following. So if F from X to T is a smooth family, then the rational locus.
Can I ask something?
Yes.
So if we work over the complex numbers, then this xt is geometrically rational is only a condition, an actual condition at a generic point, right?
Yeah, I mean, a non-closed point. So T could be bigger, not just a curve. We could look at families over a surface or families over a bigger dimensional scheme. And then this condition becomes relevant over the non-closed points.
Oh, okay, I see. Yeah. Okay, but over the closed point, okay, it's already clear.
Over the closed points, so you don't need to worry about that. Yeah.
Okay. All right. Thank you.
Okay. So if you have a smooth family, then the statement is this rational locus is a countable union of closed sets. I mean, it could be empty, it could be a finite union, so it could be a closed set inside T. But in principle, it could also be a countable union, where you have actually really need countably many closed sets to take the union. And maybe as a personal remark, let me actually mention that the question, I learned this question, or this conjecture, whether this was true, from Paolo Francia when I was a student in Geneva. And so Francia suggested two questions that turned out to be kind of hard questions. This was one of the two questions. Unfortunately, this theorem actually, I wasn't able to prove it. So we're going to use this theorem from two properties. The first one is a general property, which surprisingly was not in the literature. So this is something that I did with Davide Fusi. Is that it says the following: for any family f from x to t, the rational locus of f is a countable union of locally closed sets. So that the difference in the statement is that these sets are not necessarily closed, they're locally closed. So what is missing here in order to get the theorem is to show that if the family is smooth, then if I take a degeneration of rational varieties and the limit is a smooth variety, then the limit is also rational. And this is a theorem due to Kontsevich and Shinko. It says if f to x to c is a smooth family over a smooth curve, and the generic fiber, x eta is rational, then so is every closed fiber. Okay. Of course, the rationality of the generic fiber will be over the function field at the generic point, which is the function field of the curve. And then the conclusion of every closed fiber is rational will be over C. Okay, maybe just say this. This will be over K, which is the residue field at the generic point. And this will be over C. Okay. So if you combine these two theorems, then we'll see. It's not hard to see that these two properties together imply the main theorem as stated first. Okay. So maybe the question I want to ask is this theorem, maybe call this the main theorem of today. Is the main theorem optimal? Or is just what we can prove? So let's just think of maybe put some remark here. So, let me go back, sorry. Let me introduce one more notation. I'm gonna let n be the relative dimension of f. So this is just the dimension of any fiber. Okay, and that will be noted by n. Okay, so if the variety is a dimension at most 2, then what do we know? Well, you just rationality is characterized as smooth families by some vanishing of some cohomologies. which are constant in the family. So we see that then the rational locus is open and closed if F is smooth in the smooth family. So it's either everything or nothing if the base is connected. So you don't need countably many subsets to take a union. However, in another dimension, there is an example. It was actually very hard. It's very hard to construct an example with countably many things. And in fact, it's very hard to construct an example of a smooth family which has both a rational fiber and a non-rational fiber. This is actually a kind of a classical question. So while I haven't been able to trace in the literature much about a general structure theory like countability and so things, certainly the question on the generation, that's something that already appears. People have looked at like 100 years ago. I think Morin and Fano, among others. But finding a smooth family which contains both, or a connected base which contains both a rational and a non-rational member has been a challenge. And this was actually an open question until very recently, even though we have a, let me say, so there is finally an example by Hassett, Pirutka, and Schinko, which implies that the theorem is optimal. So do you really need countably many? Is really a countable, infinite countable union of closed subsets. So the rational locus is not closed in the smooth family. So I will not talk about this result. But let me just mention that, in fact, has been long expected that cubic fourfold, maybe let me add one word, smooth cubic fourfolds should provide such an example. Okay, so let me just mention two names here. Hassett, in his thesis, he constructed countably many family, in dimension 2, I think, of rational cubic fourfolds. Among the cubic fourfolds containing a plane, there's some Hodge theoretic argument and some explicit construction and interpreted Hodge theoretic arguments of rational cubic fourfolds. And then the speculation eventually was formalized from a slightly different point of view by Kuznetsov, using derived categories, which give a precise conjecture, tell us which cubic fourfold are rational and which cubic fourfold are not rational. And according to this conjecture, cubic fourfold should indeed give a counterexample. But this is open, but this is still open. In fact, we don't even know that the general cubic fourfold is non-rational. This is still open.
Tommaso, what is the dimension of the example of Hassett, Pirutka, Schinkel?
Yeah, I think it's 4 also. I meant to look it up and then I didn't. I think it's also 4-dimensional.
So for threefolds, it's open.
I don't know what is known for threefold. I don't think anything is known, but I would have to check. So kind of I go by memory. Yeah. Okay. So with these remarks, now let's address the the theorem. So again, let me go back and scroll back. So the main theorem here, I want to prove that on a smooth family, the rational locus is a countable union of closed sets. And then I'm gonna first give this general structure theorem on arbitrary families. And then I will focus on the Kontsevich-Shinko theorem about specialization in smooth families of rational varieties.
Tommaso, can I ask you another question?
Yeah.
What about the unirational locus?
I was going to mention something in a moment, but I can mention it now. So, so if you look at this proposition here, I can replace the word rational by unirational, and the proof carries through in the same way. So we know that for an arbitrary family is a countable union of locally closed subsets. However, the proof of the Kontsevich-Shinko theorem, it doesn't seem to work, at least not in an obvious way, for unirationality. So I don't think it's known that a smooth specialization of a unirational variety is unirational. I think that remains an open question. Now we talk about the first proposition, countable constructibility. For the rational locus. Okay. So the statement again is that the rational locus of F is a countable union of locally closed subsets. So the proof here, actually our original proof was a bit more complicated, but this proof was actually just by Voisin. So first, let me fix a notation. Let me call P the projective space over the base T. So if you like, just a projective space cross T. Okay, and then we consider a fiber product X cross TP with a projection to X, a projection to T. Sorry. And a projection to P over the base T. So the idea here is that if I give you a closed set inside the product, then for every T inside T, such that when what I can do is that I can look at the base change. So I'm going to look at the fiber of the point T, and then I look at the fiber T over here. And so this gives a correspondence between XT and PT. So if I have that the two projection map are birational, then of course this implies that T belongs to the rational locus. So this is the rough idea. But to look at these correspondences inside X cross P and try to argue about that. But so maybe one thing to mention here is that we're going to have to do this by also base changing over T and on the base T, which come out automatically with the proof. And then again, if I replace this word birational with the word dominant, then I characterize unirationality. So with this in mind, what we're going to do is I will look at the Hilbert scheme of this product, the Hilbert scheme over T, so it parameterizes schemes in the fibers, one way of thinking about it. And then if I pick up V in a reducible component, then I can consider the following base change. So let me actually write it again. We have this map here to T. And here I'm gonna base change to P to V. So there is a map here from V to T, the construction. So base change, and of course the base change the whole X cross V over T and P cross V over T. And then there is a universal family. Let me rewrite V here. And there's a universal family which is a close-up scheme of this product. Okay, so for every V, then I look at the following set, S sub V, to be all the points in V, such that when I look at the map, when I base change at the point V, the map here, where the fiber will be XV, base change of some fiber XT to V, and here going to have a PV. And I ask, and this is birational, and this is birational. And these properties are constructible. So this is a constructible. In V, and so is G of SV, if I go to maybe GV, this map here. And then we conclude by the fact that the rational locus is just a union of these things. Because clearly this establishes a rationality up to some base change of the fibers. Conversely, if a fiber is rational after some base change, which I always can take to be finite, then I'm going to pick up an element in the Hilbert scheme. And then, so this proves the constructibility because the Hilbert scheme has countably many irreducible components. And that's where the countability comes in. Okay, any questions on this one? So let me then move to the second part, which is the more interesting one. So let's talk about smooth specializations of rational varieties. Okay, so let me recall the theorem of Kontsevich and Chinko. So they will start with a smooth family. Over a smooth curve. And then if the generic fiber is rational, then it implies that the closed fibers, all fibers, are rational. Okay. So I need to give some definitions now before we put this theorem. But maybe before I do that, so the idea is to give some define some general ring which somehow capture rational varieties or varieties up to birational equivalence over some field, and then actually just maybe just define as a group here. In this group of we're going to have a specialization map, and then and that will improve the theorem. So this kind of specialization maps, they already been studied a lot in, for instance, in from a point of view of motivating integration and the Grothendieck ring of varieties. Maybe I mention more about this at the end. But somehow those approaches, they say something about stable rationality, but not quite about rationality. But all I want to say here that if you're already familiar with the Grothendieck ring of varieties, what you think about here is that this is some sort of version of it, which is better suited to understand rational classes of varieties. So let me start with the definition. What is the Burnside group? Of a field. Okay, so this will be the Grothendieck group generated by isomorphism classes or finitely generated field extensions. L over the ground field, which is K, over the field, given field K. So an element can be seen as a finite linear combination of classes, or this isomorphism classes, where the coefficients are just integer numbers. And in this group, we have that if I give you two extensions, they define the same element if and only if this extension is isomorphic over K as extensions. Okay. And in particular, by this description, you see that there is a natural grading given by transcendence degree over K. Okay. So a way of thinking about this is that you can think about this geometrically. If you're thinking about the Grothendieck ring of varieties, you can think about similarly here. This would be generated by rational classes of varieties, because there is a correspondence between a rational class to varieties being birational and their function fields being isomorphic. Okay. So now let me fix a smooth curve in a closed point. I'm gonna let R be the local ring and K be the function field. Oh, but let me just say. Which of course is the same thing as the function field, the curve, or if you like, the rest of the field at the generic point. Okay. So the main theorem, the key step here, again, this is Cinco, is to prove the following thing: is that for every n, there exists a group of homomorphism. Let's say, yeah, there's a group homomorphism morphism rho n is going to go from the Burns side group of the function field, so the field at generic point, if you like, to we can think of this as being associated I mean, one can actually get rid of the curve. If you complete these rings, then you get just a power series ring, and then you have a K, capital K will change, become a power series, Laurent power series. But then you can do construction from there, and you get rid of the dependence on C. But for the purpose of proving the main theorem, I think this is maybe a more concrete approach with the following property. Okay, let me put this. If f from is a kind of a script x to spec r, this germ of the curve, is a smooth, proper morphisms of a relative dimension n, then what I can do is that I can look at the generic fiber. I look at the generic fiber. I look at this function field, which I think has been a field extension over K. So this defines an element in the Burnside inside here, this element inside here. So I just take the image under rho of this guy, and the family is smooth, then I want this to be equal to the class of the function field of the closed fiber. Okay. Is this statement clear? It says, so I'm thinking about, just thinking about geometrically, I have a curve. Every time I place a smooth variety over this curve at a generic point, and I let it degenerate to a smooth variety over the special point, then I want this map to send the function field at the generic point to the function field from the generic fiber to the function field of the special fiber. But I want these things defined in general. So there are situations in which maybe there is no smooth degeneration of a given model over the generic point. So I want to define this map. Okay, so proof. We can define rho n on an element to the form L over K for some field L, L over capital K, a generic point, and extend the linearity. Okay, so given L, we choose two things. First thing, I want to choose a smooth proper model, so a smooth proper variety, X over K with function field isomorphic to L. Okay, so we make the problem geometric. And the second thing, I want to choose a simple normal crossing model. And I'm gonna say what I mean by that. C over spec R with generic fiber isomorphic to this model, to this variety X. Okay, so let me draw a picture. So I have a curve C, and really this curve now is just a thing about C being spec R. So I just have a close point and then I have a generic point. I'm just looking at these two things. So now I want to construct a model. So it's going to be some, so a model will be X, will be some regular scheme. Over R. So maybe instead of assuming that spec R, yeah. And then, so because the spec R has only 2 points, this scheme is gonna just have 2 fibers. So the generic fiber X eta is just the variety X over the function field over K. That's the field here. Over the closed points, the residual field is C. Then I want the special fiber. In general, I cannot require to be smooth. They're just too strong of a requirement. But I can always assume that I can always reduce a situation in which the central fiber is a divisor with simple normal crossing. So the special fiber will be maybe reduced. We have a simple normal crossing support. So maybe what I can do is I can write a special fiber reduced as a divisor D, and then thinking about as a divisor, I'm going to write it as a linear combination of irreducible components. Maybe say I goes from 1 to R. This is a simple normal crossing divisor. Again, the X is a regular scheme. So at every point, I can have a regular system of parameters. And I can ask that I can pick parameters. So the equations of D is monomial in those parameters. And then I look at the strata. So for every I in the set between, from 1 to R, and maybe I always assume I is different from the empty set, because that will give the open set away from the central fiber. I look at the strata di, which is just the intersection for all the I inside I, all the components di. So for instance, if I have 2 divisors, d1 and d2, and the thing in the middle, there will be d1, 2. Okay, put parentheses, that would be your I intersection. Okay, I'm gonna assume, you can always assume that the I are irreducible. It's not necessary, but it makes simpler to describe what's happening. And we can always do it by taking more blocks if you like. So the existence of a simple normal crossing model is followed by a resolution of singularities. It does take any model. You're going to have a lot of singularity. Make first the central fiber smooth, and then you blow up along the special fiber to make the special fibers also in simple normal crossing.
Tommaso, sorry.
Yes.
Usually you have to make a base change in order to make simple normal crossings, right?
No, because I'm looking here just at the reduced. So I don't care about the multiplicities. Yeah. So it could have multiplicities, but this will not affect.
I see.
Okay. So now I'm going to define for every I. I'm going to define. So for every I, different non-empty. So I look at eta I inside di being the generic point. And then I'm going to define the following field. Li will be the residue field of eta I, of eta I. But then you see, for instance, in this picture, eta I is right here. this is eta 1, 2. They might be small points in the fiber. So what I want to do is that I want to make everything in dimension n. So I'm gonna just add a bunch of variables. How many? I need to add exactly the size of I minus 1. So now this is a transcendence degree equal to n over field. So, over here, see. Okay, and now with this construction, we can now define. Now we define rho sub n of L over K. So remember what we did here. Let me go back. So K, so L was the function field of the generic fiber. And what we did, we make two choices. We first chose a variety, a smooth variety X, which has this function field, so we make it into a geometric object. And then we chose a simple normal crossing model containing that as a generic fiber. And now we are looking at the special fiber of the simple normal crossing model. And now we're using those choices to define the map. So this map will be defined by as follows. It's going to be the sum over all the I different from non-empty I's of what? I look at the classes of this field that define for each stratum. I have a field and just make it add the more independent variables to make it at the right in the right dimension. Think about this as extensions of C, and then I add them up at alternating signs. Again, I have this a size of I minus 1. Essentially, this is a kind of a codimension. Maybe make a remark here. The size of I minus 1 is equal to the codimension of the stratum in the fiber, in the central fiber. Because the index gives the codimension inside the total space of the formation, but then the central fiber has one dimension less. That's why there's a minus 1 floating around. Okay. So this is the map. I mean, maybe. Okay, now, what do we want? We want to, first of all, we want a map with a certain property that if the family is smooth, then it should give you the function field of the fiber in the middle. And do we have that? We do, because, so this satisfies the required property in a kind of obvious way. So suppose I give you now a smooth family. So this means that of course, there is a generic fiber here, and then there is a central fiber to be smooth. So in this case, the central fiber is just a divisor D. So the index is only one thing. So the only thing we have only one stratum, which is D. So now the definition of this, then you see that L over K will be exactly what we want. The stratum corresponds to the index at I equal to 1. In particular, you see that the size of I minus 1 is 0, so minus 1 to the 0 is 1. And we get exactly what we needed. So what we need to do here, we need to check that rho n, this homomorphism, is well defined. Because in order to define it, we made some choices. So we need to show two things: independence from of maybe. It's independent of the choice of model given a central fiber, and then we need to check independence of the choice of central fiber. Okay, so let me call this maybe this is A and this is B. So let's start showing. Let me just show A. Let me just explain a little bit A. B, in fact, is once we know A, it's very easy to do B. So we fixed X with function field L over K. And now suppose X prime is another simple normal crossing model with generic fiber isomorphic to X. So I have two models. So I have over, again, the curve is the base is the same, and now I have two models, X and X prime, but they have the same fiber. The same fiber here, the same. This is X. This is X. So where they differ is inside here. So maybe, so let me do it this way. Maybe this has component like this, and maybe this is some more complicated component like that. So what we get here is that we get a birational map. The birational map is defined over the base and only has indeterminacies in the central fiber. Okay, so I need to show that the definition is independent whether I pick one model or the other. So I need to be able to compare the divisor of the central fiber from one side to the central fiber from the other side. So how you do that? In general, these birational maps can be very complicated, but there is a nice structure theorem for birational maps of regular, of smooth schemes. So in dimension 2, there is a famous theorem. We just say that every birational map between two smooth surfaces, it can be factored as a composition of a sequence of blowups, of point blowups, and then a sequence of blowdowns. Basically, another way of saying that is that you look at some resolution of the map, and then that resolution, both sides of the resolution will factor as a sequence of blowups of smooth points. So that's the best you can do, right? In high dimension, there is a similar statement. You don't really know that you can actually always go up and down only one time, but there's something called the weak factorization theorem. And so what it says is that you're going to start from here, and I want to factor a map from there to here. Okay, So what it says is that I might need to go up maybe a little bit. Maybe call this 1, and then maybe I need to go down, and then I need to go up again, go down, and up and down and so on. So you go up and down a few times, and eventually you factor the original map. So what I'm gonna do is I'm gonna break. So phi will become the composition of maps phi I from some model, phi, may say phi I minus 1 to phi I, where either phi I is a blow up of some smooth center in Xi, or the inverse is a blow up of some smooth center on the other side. So this means that you're either blowing up or you're blowing down, but the nice thing is that you're blowing up a smooth center. Moreover, for each I, the central fiber may be reduced is some di, again, it's a simple normal crossing divisor, and the center of blow up from either map coming from there has transversal intersection with this boundary divisor. What do I mean transversal intersection? It doesn't mean that intersect properly every stratum. You can have excess intersection. What it means, though, is that at every point you have a system of coordinates so that the divisor is defined by monomial in those coordinates, and the center of blow-up is also defined by monomials, by monomial equations in those coordinates. Okay. I mean, we not be monomial, it would just be by some equations in those coordinates, by some degree 1 equations in those coordinates. They're vanishing on those coordinates. Another way of thinking about monomial equation is just talking about coordinate planes, coordinate lines, and those things. Okay, so we reduce to the case where the second model is just a blow up of some smooth subvariety Z inside X with transversal intersections with the boundary divisor D, with the central fiber. So this is more manageable. So I'm going to denote by d prime will be d prime 0 plus the sum from I goes from 1 to R di prime. So this is the exception divisor of phi, and these are the proper transform of the corresponding di. And by the way, maybe I should mention the subvariety is contained in the central fiber, because outside on generic fiber everything is smooth. I don't need to blow up. That would be a necessary thing to do. Any questions on this step? This is kind of a standard thing to do with the application of the weak factorization theorem. So now So we just need to check that whatever center we are blowing up, as long as this nice transversal intersection with the boundary divisor, will not change the definition of rho. So okay, using C, we defined some rho map from now. If I use instead the model X prime, we're going to define a similar map. Let me just denote it by rho prime. It's still a group homomorphism from the same groups. But it uses now D prime instead of D in the definition. So we need to check that we are defining the same map. The expression itself on a nose is different because D prime has more components, so we're going to have more strata. So the sum in the definition of rho prime is going to have more terms than the corresponding sum in the definition of rho. What we need to argue is that there are cancellations so that the sum reduces to the previous sum. The rho prime reduces to rho. So we can write this explicitly just with index sets. And I find it personally a bit confusing to trace exactly which index set how to write. So there is maybe another way of visualizing the same computation using dual complex. So we need to show that rho prime of n of L, let me just write it this way, is the same thing as rho n of L. So we can visualize this using dual complexes. Okay, so maybe as quick parenthetically, what is a dual complex? If I start with D, a simple normal crossing divisor in some smooth variety, which has some components di, and then I'm going to assume that the strata remind you, this is the intersection of the divisor indexed by I assume that when I look I different from 0, it's irreducible. Okay, so how you construct a complex? I want to associate a CW complex, which is denoted by delta D, which is defined as follows. So every DI, every reducible component will define a vertex DI. So abstractly, I put a vertex for each component. Then every time I have a Dij non-empty, I put an edge between Vi and Vj. And in general, to each stratum, non-empty stratum, I put a face, an open face, sigma I, in the right place. And of course, inclusion between the strata, or if you like, reverse inclusion between the index sets, will determine the gluing of these faces inside the CW complex. For instance, I just say I have two divisors like this. If I have two divisors, then I see that I have one vertex for each divisor. It's since they intersect, I'm going to have an edge. And I suppose maybe there is a third divisor right here, where there's going to be a third point. This divisor intersects both things. So there is but then there is a point of intersection of the three divisors that will give the inside a face, two-dimensional face. Like that. So this is D, and this is delta of D. Okay, so now we can think about what's happening here. So now we have Z inside D, some smooth transversal center. And you are blowing that up. And we want to understand. So, and then we blow up Z, and we get a new divisor D prime. And so we want to compare delta D prime to delta D. Okay. So there are two cases here we want to study. So two cases. So the first case is when Z is equal to a stratum di of D. So for instance, I have on a plane, I blow up the origin when the simple cosine divisor is given by the coordinate axis, and I just blow up the origin. So what happened in that case? So well, let me maybe find an example. So for example, so maybe I have 3 divisors. You know, there might be more divisor outside and so on, right? In principle, there may be more things, but I focus on these 3 divisors, and maybe the center is a point here. Suppose that Z is this point here. So what happened when we blow this up? So let me actually move this a little bit. And let me actually remove these additional divisors. Okay. So there may be more divisors outside, but locally, I just look at what happened around that point. So when I blow up that, I'm extracting a divisor right in the middle. So I have this new divisor in the middle, which is what I call D prime 0. Okay. So let's see what happened to the dual complex. So the dual complex, the one below, is something that I already said what it is. So let me actually draw it a little bit bigger. There is a point for each divisors. There are 3 edges, and there is a 2-dimensional face, which this time I'm not going to highlight anymore, but there is a 2-dimensional face right in the middle. When I blow up, the 3 divisors, they still intersect each other, right? You see, I didn't eliminate this intersection. So they're still there. So I still have these 3 divisors here, and they still intersect like that. But now I need to be careful because they don't have a common face. There is not a face because there is not a common point of intersection of those 3 divisors anymore. Instead, they're going to be some divisor D0 prime, which corresponds to a new vertex in the middle. And now everything intersects D prime 0. So there are segments like this. Okay. So one way of thinking about this is that there is an inclusion going this way. And in fact, this is an identity on a support on the underlying topological spaces. And what I did here is that I made a refinement of this, or the triangulation, if you like, or the CW structure. I added a vertex, and I cut down a face into 3 faces, and so on. So this cycle is called, has a name. It's not a barycentric subdivision. This is called a stellar subdivision. A barycentric subdivision of this triangle would also have introduced vertex here and these edges. There would be a barycentric subdivision. So this is called a stellar subdivision. The fact that these two spaces actually topologically or set theoretically are the same space, there is a natural way of arguing that. So the dual complex itself can be naturally thought as a set of evaluations on the variety, or the model in this case. Because clearly every point here corresponds to evaluation. But now I say, okay, what is the middle point here? Well, the middle point here will be the evaluation if I blow up this edge, that exception divisor, maybe a point or coordinate of ratio 1/2, 1/3, or 2/3, 1/3, so maybe I break it into 3 parts. All of that can be described using Tor evaluations, monomial evaluations. Even in rational way, they still define evaluations. So every point in here is itself evaluation. And in fact, every point inside is evaluation. The middle point, the barycenter of the triangle, is exactly the evaluation I get extracted by blowing up. And this is what I draw here. So there is a very natural identification. There is a natural location of this point inside there, if you just think about this from the point of view of evaluations. Anyway, so now we need to argue that.
Sorry, can I ask something?
Yeah.
About this stellar subdivision. So in the upper thing where we blow up, so it still has a face. So how do I picture this? So I have this point in the middle, but do I have like faces everywhere now, or?
Yeah. So I didn't draw the faces, but so here there was one two-dimensional face, and here now we have 3 two-dimensional faces.
Okay.
And the maximum dimensional faces that correspond to these 3 points, which are the smallest strata. Now, before there was only one zero-dimensional stratum, and now we have 3 zero-dimensional strata.
Okay, but the bottom face somehow is still missing, so it doesn't have a face everywhere.
This point is gone, so this face does not exist anymore. It's been replaced by these 3 faces, 2 edges, and 1 point. But that's exactly what is going to come up in the computation. Because before we were using this face it was one of the terms appearing in the definition of rho. This face give you a field. So let me give you some name. Let me call this face sigma I. So sigma I was giving us a field Li. But now we don't have a sigma I anymore. So that term in the sum is gone, has been replaced by what? By a bunch of new terms, which are given by some other sigma prime j. So these are new faces that didn't exist before. And there are how many of them? There is 1, 2, 3, 4, 5, 6, 7. Okay. So these new faces, I need to argue the new faces give the same sum. So maybe for each new face sigma prime j or the dual complex of d prime included is contained in sigma I. By when I say contained, I'm thinking about the underlying topological space is contained as a subset in sigma I under this interpretation, if you like, using evaluation spaces. We have that the corresponding L prime J is actually isomorphic to Li. So for this, that requires, maybe that's not completely obvious, but it requires seeing what's happening here. So let's just think for a second about this. Let me argue that for a moment. So let's look at the geometric picture. So here I have, well, in my picture, this was a point, but suppose that now this picture is bigger dimensional. So this maybe represents some some center, some stratum which has its own function field. And then to that, I add a bunch of free variables to reach dimension n. Now, what I do is I replace now this point by what? I have 3 points here, I have 2 edges, and I have a divisor. 2 lines, 2 other strata. So there's this 7 strata, which are the 7 faces that I counted here. So these 3 points here, actually, these 3 strata here, they're actually isomorphic to Z. So because they're isomorphic to Z, they have the same function field. And then when I add the 3 variables, still have the same field. How about this stratum here? Well, this stratum here is gotten by blowing up this point inside this divisor. In any case, it's going to be some fibration over this stratum. So this stratum is going to be some fibration over this stratum, and the fibers are open set in a projective spaces. In fact, they are open set in P1s. And this will be the same thing. Over here will be an open set inside the fiber, will be an open set inside P2. So all these fibrations coming from the strata here to this stratum, they're all fibrations, smooth fibrations, where the fibers are open set inside projective spaces, because these are just blow-ups of a smooth center and a smooth variety. So I will understand those fibers very well. So all those fields, up to adding some free variables, they're all the same field. I haven't changed those fields. So I replaced one face by 7 faces, but all those faces contribute to the definition of rho with the same field. So now it becomes just a matter of counting. So we're left to do I'm going to say that J, I'm going to use this symbol for this condition. So what we're left to do is just to check that when I look at the sum for all the J, we say dominating I, meaning that the faces are inside there, of this -1 to the J -1 is the same thing as -1 to the I, to the size of I -1. Well, what is this? This essentially is just a statement. Of course, this can be computed directly. It's easy to compute directly. But this is just a statement that in order to compute all the characteristic of a topological, topological manifold, I don't care which triangulation I pick. A chain triangulation is the same order characteristics. And that's what this statement boils down to. Okay. So this is kind of a sketch of the proof. It's not really precise because more faces I need to look at. It was just an example. But in fact, all the cases can be interpreted this way. So this was the first case, right? So this is when I blow up a stratum. So I didn't change the set, the underlying topological space of the dual complex. I just made a refinement of it. And then I just argue that all the characteristic is independent of the refinement, or the CW structure, or the simplicity structure of our topological space. So the second case is when Z is actually different from any stratum of D. So what happened here is that because I don't blow up a stratum, I don't eliminate any phase of so okay, before we eliminated a phase because we blow up the corresponding stratum, so that phase was gone. But now we are not blowing up any stratum. So all the strata generically, the generic point of the strata has been untouched by the blow up. So it's still there. All the intersections are still there generically. Maybe the strata is a bit smaller, but it doesn't matter. The combinatorial point of view of those intersections remain. So the dual complex of D hasn't changed. So what has changed? So instead, sorry, read this. The dual complex after the blow up is obtained by adding new faces. So let me explain this in a couple of examples. So let's see, the first example I can do is the following. Suppose I have two divisors like this. Okay, so maybe say D1 and D2. And now Z maybe is a point in here. So you notice that now Z is not a stratum because I don't have a divisor cutting that point out. Z is contained. Z is contained in this stratum. Is also contained in the closure of this. All my strata are closed here, so it's contained in this stratum, in this stratum, and in this stratum. So it touches all those three strata. Maybe there are other divisors here that I'm not picturing. Maybe, oops, wrong. Ah, boy. Maybe there are other divisors here that I'm not picturing. So now let's look at the dual complex. The dual complex of D, in this case, there is this one segment here, and maybe the dual complex continues. I don't care. But now what do we do? In yellow, the dual complex of D prime is obtained so when I blow up this point, okay, maybe I need to draw the picture here. So what happens when we blow up? Oh boy. It introduce this new divisor there. So this is my D0 prime right there. This way. So this is delta prime. This is D. Okay. So what happened here is that let me redraw this picture here. So I haven't touched there's going to be an inclusion here. And this is really an inclusion of CW complexes, meaning that every phase is going to be included as a phase, as a combinatorial phase inside the other one. What I did is that I added a new vertex here, B0. And now, well, this zero intersect this guy and the intersection. So this means that this V0 is going to have an edge here, and then I'm going to have this face here. So what I did is that essentially, well, another way of thinking about this is that this intersection determines, this is some subcomplex of strata meeting Z. And this guy here is just the cone over, let me call this a complex sigma, the cone over the sigma. I add a new vertex and I just build up a cone out of it. Okay. And now here you need to be a little bit careful about understanding, because I could also have a situation like this. Let me maybe draw another picture. Maybe you could have a divisor D here, and maybe another divisor here, and a divisor here, and maybe this time I blow up this center. So let me draw this, a picture here in one go. So here I have something like this, a chain corresponding to those three divisors, and maybe continuous, because maybe this divisor is continuous. And what I did here is that now I have a new vertex here when I blow up Z, and then this intersect all those three divisors. So I'm going to have three segments, and then I'm going to be these two faces here as well. So I need to add those things. So now here I need to make an analysis of what's going on. The point is that there is a combinatorial retraction or collapse of the delta D prime into delta D, but I need to tell you combinatorically where the faces go. So in this case, for instance, the generic point of Z it only intersects this divisor, so there is a retraction like this, and then this retraction is not canonical. I just need to pick it up, but the combinatorial part of it is determined by the fibration. Maybe to understand this, you really need to look at the fibration on the strata to see what's going on. In this situation here, this goes down this way, these faces go down this way. But at the end of the day, what you notice here is that I reduce a similar computation where now I'm adding all the terms coming from these pieces for new faces, and all I'm claiming here is that the alternating sum of those terms is equal to 0. And I need to argue that the fields are they're gonna match again. Okay, so sorry, this is a bit sketchy, but that's the idea. So in the last 5 minutes, any questions? I wanted to go back and just finish the proof of the main theorem now. They're ready to do. But if any questions, is this clear enough? Maybe I explained the first case a little better, I think. Let me now move on and do the proof of conserving single theorem, which again, it states the following thing from X to C. So be a smooth family. Over a smooth curve. And then the generic fiber is rational. This implies that every closed fiber is rational. Everything. Okay. So what I'm going to do is I just fix one point. A close point. I call it 0 now. And then again, you're going to let being the local ring at 0. You're going to let L be the function field of the generic fiber. Okay. So now what do we know? So the fact that X is rational, or maybe I should say, and then I'm going to let curly X to be the base change of the family spec R. So now I have this model here of spec R, and this is a smooth model of spec R because it's base change from a smooth map. So the generic fiber of this model is the same thing as X theta. So this is rational. So it's birational to some Pn over capital K, over capital K. Well, that's the same thing as saying that the simple normal crossing model is birational to Pn over R over R. Okay? So, X and PNR are two models we can use to compute rho n of L. I have two models, and then what happens if you use one, and what happens if you use the other? So using X, what we see is that this rho n of L over capital K, well, because there was a property in the previous theorem, that this specialization map, it should give you the function field of the central fiber if the central fiber is smooth. But the central fiber for this model X is smooth, and is exactly X. So this will be the fiber, the function field of the central fiber, which is the same thing as X naught over C. On the other hand, if we're going to use this projective space as a model to compute the same map, we see that the specialization of L will just be the function field of a projective space. So therefore, X0 is rational. And that's at the end of the proof. Okay? Okay, so because the rationality of the generic fiber just allow you to pick up these two different models. One is a kind of a flat, I mean, it's just a constant model of projective spaces. Another one is the one that generates into X0. Okay, so that's the end of what I want to talk about today. Any questions?
So I am a bit confused.
Yes.
Because you say, okay, X is birational to Pn over R. Pn over R is a product, right?
Yes, Pn over R
is a product.
it's the same thing as Pn cross spec R.
That's right.
Because they're the same generic fiber.
So this is because R is a local ring.
Yes.
Right? That's because R is a local ring.
I mean, no, not really actually, but
because otherwise, I mean, you cannot. If you have a family of rational varieties, right? So
I see what you want to get. Well, what I want to say here is not that the condition here is a little bit stronger. I'm assuming that the generic fiber is rational over the function field of the base.
Mm-hmm.
So I'm not asking that it's geometrically rational. I'm asking actually it's rational.
Mm-hmm.
So that's a stronger condition.
Mm-hmm.
So if only the closed fibers are rational, then of course I don't know that the total space is birational to a part of a projective space.
Right, right.
But if the generic fiber is rational, then they are birational. I mean, one way of thinking about this is that the function field
they have the same generic fiber.
The function field of the generic fiber is the same as the function field of the total space.
Right, right.
So if I look at the generic fiber the generic fiber, the function field of the generic fiber is isomorphic to the function field of projective space.
So anyway, so what you're telling me is that the trick here is that the hypothesis is very strong.
The hypothesis is very strong. So
the theorem doesn't say that if every closed fiber is rational, then so if there is an open set such that the closed fibers are rational, this does not imply a priori that also some specific closed fiber is rational.
Not directly, but it does imply it indirectly. So the point is that okay, let's say we work over C, or in any case, over an algebraically closed field, right? So suppose that you are in a situation like the one you're saying. So I have a family, and there is an open set where all the closed fibers are rational, but I don't know the generic fiber is rational. Right. Okay, let's just say over a curve, okay, for simplicity. So the generic fiber, by this constructibility property that I mentioned first, the generic fiber, this field is uncountable, okay? So the generic fiber has to be geometrically rational. Just think about, again, the example of the pets of a P1. In general, a generic fiber is not rational, but it will become rational over the algebraic closure over the function. Yes. Once it's rational over algebraic closure, then I only need to add a finite number of, a finite extension, and then we become rational. Just add those coefficients determining the rational map to Pn. So this corresponds to a finite cover of the curve or the base. So this means that after taking a finite cover of the base, now I base change to a new curve, which has a covering map of the original curve. And over this base change, the generic fiber is rational.
I see.
And then I can apply this theorem. So this is actually how you apply this theorem to prove the main theorem I mentioned at the beginning of the lecture. The fact that this locus of rational fibers is countable union of closed sets.
I see.
Yeah, you need to allow. Yeah. So the assumption here is very strong at first, but then you can there's a lot of freedom in which you can apply it.
I see. Okay. So I have another question which is weakly related to all this.
Yeah.
And namely the following. So suppose that you have a flat family such that the generic fiber has a certain codiary dimension. Okay. Then you take the central fiber. Can you say that every component of the central fiber has codiary dimension less than or equal than the codiary dimension of the general fiber?
Oh, I don't know. I mean, of course, there are. I would like to look it up a little bit. Yeah, I don't know. I don't know what is known. I mean, for smooth fibers, for smooth fibrations, then I think stating like invariance or plurigenera.
That's right.
Will imply something like this. But if you have, that's
no, it could be very bad, the degeneration.
Yeah. That's a good question, actually. Yeah, I don't know.
Okay. That seems a very natural question.
Yeah, absolutely. Yeah.
Okay, good. Thanks.
Are there other questions? We stop the recording.